So okay guys, this is the second class of that linear system theory, and the previous class, for refreshing your mind, let me increase the voice. Okay, so if you had the linear transfer function in the form of p0 Sn plus p1 Sn minus 1 plus Pn and over Sn plus A1 Sn minus 1 until An. We said that we have four types of the state space representation. The first was the canonical form that we were writing as this, if you remember from the previous class: x dot 1, x dot 2 until x dot n minus 1 and x dot n, because this is the LTI system, linear time invariant systems. So, and this is controllable, this is the canonical form. That's right, canonical forms. So it is 0, in the previous class we wrote like this: 0, 0, 1 and 0, 3, 1, 2, 3, 1, 2, 3, and the x n minus 0, 0, 0, 1, and then from here we have minus an minus 1 until minus a1, and obviously multiplied by your state variables x1, x2, xn minus 1 and the xn, that's right, plus bu, that's right, bu. So this is, as I talked in the previous slide, this is the B matrix for the SISO system, and this is that A matrix, that's right, we get it. And then the output is based on transfer function. The output is Pn minus An multiplied by B0, Pn minus 1 minus An minus 1 B0, and finally P1 minus A1 B0 in state vectors x1, x2, xn, that's right, plus b dot u, b not u, not b dot, b not u. So this is canonical, that's right, canonical form, as I said in the previous class, that's right. This is the first type of that state space representation. So the second form, I'm gonna give you an example after I'm done with the four types of that representations. Okay, the second form is 2 is observable canonical form. Okay, so as you expect now, it's gonna be this side x dot 1, x dot 2, x dot n. Now this matrix A is transpose of the controllable canonical, sorry guys, controllable canonical form, that's right. So the observable canonical form is the matrix A is like as the A transpose. So it's gonna be 0, 0, 0 minus A0. See that? Like as the transpose, this goes up. Understand? So 1, 0, 0 minus A minus 1 dot 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 0, 0, 1 this. So right, if you exactly transpose this matrix, you're gonna get what? That one, right? So and in the state variables, x1, x2, and the xn, that's right. Plus, now the b vector gonna be, look at here guys, here, look at here, we are just make this the transpose of this, so putting here bn minus an b naught, bn minus 1 minus an minus 1 b naught, and coming down b1 minus a1 b naught in u. Okay, why? Because we're writing like this, because we have only one input, one output. So CISO system is right. So, but it's u, it's y, the output. Okay, if you look at here, I'm just using this, but transpose of this. See, that's a flip between the controllable canonical form and observable canonical form. So it's gonna be 0, 0, 0, 1 in state variables, that's right, plus b dot b not u. You see the output, that's right. Understand? So we learned the controllable canonical form. We transpose the A matrix of this for introducing that the observable canonical form. I'm gonna talk a lot about the controllability and the observability in this course. That's right. So just bear with me, okay? So the third form that you have to know is what is hold on, some birds they are screaming. Okay, the third form is tree is diagonal canonical form. Diagonal canonical form. So it says we in this form assume that transfer function denominator polynomial includes only, I'm changing the color to emphasize, distinct roots or poles. Remember that, for example, if you go to the vibration course that I was teaching or undergraduate control, so we had the critically damped system. Critically damped system is a system that you have a repeated real pores, that's right. So the critically damped system cannot be extended to the diagonal canonical form because it has a repeated rule. So we need a transfer function that is polynomial, is characteristic polynomial, only includes distinct poles. Okay, so on the other hand, y over u, if this is the transfer function as we had here, b naught has distinct poles. So S, like as if I want to give you just a trivial example, this is underdamped systems, right, or overdamped system. So they have the distinct poles, that's right, like as a pair of complex conjugate poles, right, from undergraduate control or the vibration course that you passed. So you have n distinct poles or roots. So now you can write this, or you can decomposed to in the following form from algebra. This is not control. It's right from high school algebra. Plus Cn Spn. So you see that you have distinct poles, right? N distinct poles. So if you have that, so diagonal canonical form can be written as this: x dot 1, x dot 2, x dot n for nth order system. That's right. Minus p1 goes to 0, and you only have what? Diagonal elements, as its name implies. That's right, and the 0. So here we go. So it is x1, x2, and the xn. That's right. Plus 1, 1, 0, 0, 0, 1. That's right. U. Understand? So you're gonna say, what's the advantage of this formation? Because you know that if you want to calculate the determinant of this matrix, is only multiplication of the diagonal elements p1, p2, p3, pn. It's very simple. That's right. If you want to calculate the eigenvalues of this matrix, that you have to do it 100% eigenvalues, and you will understand in the designing the controllers. Eigenvalues I will teach you. Okay, eigenvalue is going to be p1, p2, and pn. Understand? So it's why the output gonna be from here, from this equation. This constant c1, c2, cn in the state variables, obviously x1, x2, xn plus b dot u again. So this is the third one. The third one was controllable canonical form. Second was the observable canonical form. Third one was diagonal canonical form. If our transfer function has distinct poles, then we are decomposed to this form and we get the general formation. Recording. Yes. Now we can go to the fourth one and the last one. Right? So the fourth one is 4. Jordan canonical form. Okay. If transfer function includes multiple roots. What's the meaning of that? Okay, means pi's, that the poles are different from each other, except that, okay, the first three poles are repeated or equal. Means P1 and the P2 and the P3, we have repeated poles. Right? So now you can write your transfer function as before, b naught Sn minus 1 Sn, that's right, plus b1 Sn minus 1 and continues bn divided by S P1 cube, because they are repeated poles, that's right. Now S plus 4 2 what? S plus Pn. So you have three repeated poles, the first repeated poles Here we go. If that's the case, you can represent your state space equation as the Jordan canonical form. Okay, so now you can expand this as this. Look at here, guys, from algebra, that's right. C1 S, oh, hold on, guys. Okay, S plus P1 cube, remember undergraduate control, C2 S plus P1, this is algebra from high school also. This is how you decompose a repeated poles or the polynomial, that's right. C3 over S plus P1 plus finally, Cn S plus Pn. Okay, so state space representation in the Jordan canonical form, these are your state representations, gonna be interesting one. So if you have three repeated poles, okay, here you're gonna have minus P1 1 0 0 minus P1 again, because they are repeated, they are equal, 0 0 minus P1, and this section of that gonna be 0 0 0 and 0 0, that's right. And here gonna also you have 0 matrix, right? Here you P4 starts, P4 0, that's right, and diagonally come down to the Pn 0, and this is how you write your A matrix in the Jordan canonical form. So your state variables, that's right, plus your B is different from the diagonal canonical form, that's right. It is 0 0 1 1 1. So the first two are the zeros and the U. The first two are zeros and the rest are 1. And the output, like as the diagonal element gonna be C1, like a diagonal canonical form C2, and the Cn x1 x2 and the xn plus b naught u. Understand? So these are the things that you don't have to just memorize it. You can find in any published books or just in the Wikipedia. Okay, these are standard formulations of the state space representations. Okay, example. Okay, suppose you have this transfer function. Output over input is s plus 3 divided by s square plus 3s and the plus 2, right? So obviously you can write as this, guys, 0s square plus s plus 3 and the s square plus 3s plus 2. So based on, if you compare this, guys, with this, so your b naught is how much? 0. Your b1 is how much? 1. And your b2 or bn, because your system is second order system, guys. Your system is second order system. Okay, that's right. It's 3. So comparing that, you get b naught is 1, b1 is 1, sorry, b1 naught is 0, b1 is 1, and b2 is how much? 3. So again, comparing this with that, you get A1 is how much? You get A1 is 3, and the A2 is how much? 2. Understand? So in the controllable canonical form, I'm saying that CCF, okay, the first case. So what, because your second order system, S square is x, you're gonna have two state variables, x dot 1 is equal to x dot 2. That's right. So you have two state variables, x1 and x2, because your system is second order system from undergraduate control. That's right. And if you look at it, you're gonna have 0 and 1. That's right. So 0, 1. The last line of that is starting from minus an from this side to this side, right? So you're gonna have minus 2 and minus 3, obviously. Plus, this is your A matrix, as I talked to you, plus BU. Its B is 0, 0, 1. So, 0, 1. Here we go. Okay? This is controllable canonical form. So its Y is what? Bn, here B2 minus A2 minus multiplied by B naught. So B2 is 3 minus A2 is 2 multiplied by B naught, 0. That's right. Now the rest. Bn minus 1 minus an minus 1 in B naught. So 1 minus 3 multiplied by 0 in what? Again, x1 and the x plus B naught in u. B naught is how much? B naught is 0. 0 in u. So the output gonna be what? The output gonna be 3 and 1. Get here, 3 and 1. Right? And x1 and the x2. This is the output of the system, that's right. Or if you want to just summarize it, it's gonna be 3x1 plus x2 in the controllable canonical form. Now, guys, everything, hold on. So if I now extend that the observable canonical form, right? So I taught you that it's enough that you transpose A matrix. Remember, look at here. Here was the A matrix. If you transpose this, I taught you this row comes to the column of here, right? So on the other hand, if you look at here, if you transpose this, you're gonna have 0, 1, minus 2, minus 3. Here we go. You don't need to generate again everything, that's right. You don't need to invent the wheel. Plus, and I told you, you use this in the column version for the observable canonical form. So because you already calculated this here, 3 and 1, you have to make it column. So 3 and 1. Here we go. Simple like that. Okay? Understand? So if I say A of observable and A of controllable, so I said that A of observable is A controllable transpose. That's right. This is the golden and important simple mathematics between them. That's right. So, and it's Y, the output, look at here, here's what's this B. If you use the B and make it column, you get the A. So the same here, transpose of that. You're gonna have 0 and 1, see? I make the column of this, row of this, is right? In x1 and the x2 plus again b naught u. Look at here in the observable, b naught is 0, so it's 0 plus 0. Understand? So I developed the controllable canonical form, its output, observable canonical form, its output. Now my question is, can I generate the Jordan canonical form? Can I? So can I generate the Jordan canonical form? The answer is no. Why? Because I taught you the Jordan canonical form, guys, is when you have the first three poles are equal. So, but the poles of this transfer function, the poles are found from the characteristic equation. So that here is s square plus 3s plus 2 is 0. So the poles of this from algebra high school is minus 3 plus minus 9 minus 8 divided by 2 minus 3 plus minus 1 divided by 2. So the poles are how much? Minus 2 and minus 1. So they are distinct poles. So they cannot represent by the Jordan canonical form, but you can extend by diagonal canonical form, because all of the roots are what? Are distinct. That's right. Minus 1 and minus 2, obviously. That's right. So, but as I said, you have to do like this, right? So so because we found this, so this is the diagonal canonical form. So x dot 1 and the x dot 2 based on whatever I taught. Get here, guys. Oh, here it is. Only on the diagonal elements they are the poles. Look at here, this. That's right. So you're gonna have minus 1, 0, 0, minus 2. Okay, from this like that. So in x1 and in x2 state variables. So, and its B matrix is 1, 1, 1, everything is 1. So plus second order system 1, 1 in U. Okay, so it's why if you calculate that, look at here, guys, you have to do based on this. You can see here, you have to do like this. If you do that, I assign as a homework, please do it. The y gonna be 2 minus 1, means c1 is 2 and c2 is minus 1 in x1 and the x2 plus 0, because b naught again is, because b naught is 0. We calculate, see, b naught is 0. Understand? So please derive this as homework. Do it. Okay, do it based on this formula. Understand? So now suppose that you have this transfer function, guys, s plus 1 divided by s cubed plus 4s squared plus 10s plus 2. Okay, please you for yourself develop the controllable canonical form and the observable canonical form. Please do as homework for yourself. Okay, see if you can do that. Understand? So these are the forms that I taught you. Okay, but don't think that, as I told you, if you go to the number what is it, this problem of A91, and after that you're gonna find the proof of how this happens. But this is not magic, guys. Look at here. This is our transfer function, that's right. Now let me go to the MATLAB. Let me pause it till MATLAB comes up. Okay guys, so now the MATLAB is here. So let us go back to our example. Let's set I did this, right? So come on. Okay. Okay. So this is our what? S plus 3. S. Okay guys, look at here. If I say in the MATLAB num of the transfer function, num is 0, 1, 3. That's right, because your nominator is in the second order. See here, 1, 1, 3. So 0, 1, 3, and 1, 3, 2. That's right, and then is 1, 3, 2. That's right. So if I say A, B, this is MATLAB how it works, B, C, and D. Now from transfer function to steady state, to state space, okay? To state space, right? Understand? So if I say that, from what? From the denominator and the denominator, that's right. Here we go. Gonna give you -3, -2, 1, 0. A is 1, 1, 3, 0. Understand? So if I look at here, see that what it gives these notations to you guys. Okay, it gives you -3, -2, 1, 0, 1, 0. Okay, 1, 3. Okay, and 0. Understand? So I want to see. Okay, this gives you in this kind of notations. Okay, this is the shortcut when you are doing the research, so you have to do that. Understand what I'm talking about? Now if I say you have a third order system, suppose your third order system is I don't know, 0, 0, 0, 1, 3, means the numerator is S plus 3, that's right, and the then is 1, 3, 5, and 6. Okay, if I do that, this is a third order system, right? Here we go. We're gonna have 3 by 3 what? A matrix, 3 by 1 B matrix, C matrix, and the D. So the MATLAB does it quickly for us. Okay, so this is another thing that I wanted that you know about this. Okay, so okay, now let me close this. Okay, so now let me go here back here, guys. So guys, look at this example. Okay, I'm just writing again, and please keep this in mind: 0, 1, -2, -3. Okay, or the MATLAB one. So guys, look at here. These are not mathematics, these are trigonometric mathematics. So So our transfer function was this s plus 3 originally plus s 3s plus 2. So if I assumption is that all the initial conditions are 0 for this system, means y at time 0, y dot at time 0, and y double dot at time 0 is equal to 0. Okay, and the u at time 0 is 0, and u dot is 0, obviously. And u at time 0 is equal to u dot at time 0 is 0. So I had the assumption. So if I multiply this by this, if I multiply this by this, this is what you get. S2y plus 3sy plus 2y is equal to what? us plus 3u. That's right. If I apply the inverse Laplace from undergraduate control, that's right. So you know that the s square in the frequency domain gives you what? What? Yes, second time derivative. So you're going to have y double dot. That's right. Plus s gives you first time derivative, 3y dot. Plus 2y. Now we are shifting to the time domain. That's right. To time domain. This is frequency domain. Is equal to u dot s plus 3u. Right? Understand, guys? So now if I want to try to find this linear system, the state space transformation, is I say that x1 is y, as I taught you in the previous class, and the x2 is y dot. Remember, if I have time derivative, you're going to have x dot 1 is equal to y dot, which is equal to x2, and the x dot 2 is equal to y double dot. Y double dot is from here, minus 3 y dot x2 minus 2 x1 plus what? U dot plus 3u. That's right? Huh? That's right. Understand? So on the other hand, just if you look at here, I just want to talk about this. Okay, just look at here. Huh? So this can be written as this, guys. This part, x1 and the x2. I just want to show you. See, x1, x2. So first line is 0, 1. Second line is minus 2, minus 3. This part gives you. Now let us look at our example. This is controlled by canonical form. That's right? Understand? So it comes from here, I mean. Okay? Clear, guys? So this is another thing. So hold on, I want to see that what I can teach you. Now the next topic is, so we know that how to derive that for representation of state space equations. The next topic is diagonalization of n by n order matrix, means the square matrix, n by n, 2 by 2, 3 by 3, 4 by 4. Okay, so if we have an n by n matrix A with distinct I want to see distinct eigenvalues given by what? Given by this. Given by this. Suppose this is the matrix m by n square matrix. This matrix, guys. 0, 1, 0. Remember, controllable canonical form. 0, 1, 0. And 0, 0, 0, 1, and a2 minus a1. Okay, so this is controllable canonical form. Okay, you can make it as diagonal matrix, guys. But before that, for those of you that you forgot about the eigenvalue, I'm gonna just cover it. So before going to that, I'm gonna talk about the eigenvalue of a matrix. Eigenvalue of a square matrix. Okay. If I have a matrix A, its eigenvalue is calculated as here. Determinant of lambda I, identity matrix or unity matrix, in A is 0. For example, if your A is eigenvalue is 1, 2, 0, 4, you're gonna have lambda I. Lambda I gonna be what? Lambda 0, 0, lambda. It's a constant number multiplied by unity matrix. Minus A. A is 1, 2, 0, 4. That's right. This is equal to 0. So this is determinant of lambda minus 1, minus 2, 0, lambda minus 4 is 0. Determinant of this is the multiplication of diagonal minus multiplication of non-diagonal elements. So it is lambda minus 1 and the lambda minus 4 minus and minus, minus and 0, 0, 0. So the eigenvalue of the first eigenvalue gonna be 1, second eigenvalue gonna be 4. Obviously, this is how we calculate the eigenvalue of a given matrix. So if you go with MATLAB, I hope that you know, and I'm sure that you know for refreshing your mind. So here we go with MATLAB. Oh, MATLAB, yeah. So I'm gonna type this, and you see that the answers, they are same, 1 and 4, obviously. Then if you have a matrix that has a distinct eigenvalue, so this matrix has distinct eigenvalues 1 and 4, that's right, then you can make a diagonal matrix. Understood? So bear with me. Okay, if this is our matrix, okay, our A matrix is 1, 2, and 0 and 4, that's right, our example. Here we go, that's right. So I say Eig means eigenvalue of A must be 1 and 4, no doubt. See, it's very easy. If you have a 3x3 matrix, 1 minus 2, 3, 9, 8.5.4001. Okay, if I say I of A, it has 2 complex conjugate eigenvalue and 1 the real one. So if you are in the nonlinear control domain, I'm gonna teach you that this system gonna be unstable because the real part is positive. That's right, it's growing with the time. We're gonna talk about this later. Okay, even the real eigenvalue is what is positive. So this is another thing study in MATLAB that you had to know, and a thing that you know. Okay, then come on. So okay, so if the eigenvalues of this matrix that is in the controllable canonical form, they are distinct, you can make these diagonal. So I'm going to do that by next class, and we continue our topics.